when we want to talk about probability in any rigorous way, we are going to be talking about sets. So, for context, when we're talking about probability, our basic framework is the probabilistic experiment, and not experiment in the statistical sense. So, we're kind of overloading this definition here. But by experiment, we mean some process that's random that gives us the same range of results. So our experiment is going to give us some set of outcomes, which we call the sample space. So a good example of this is a coin flip. So it's an experiment that's well defined. It never changes, but every outcome is random. And we can get either heads or tails. But the way that we represent the sample space is mathematically as a set. And the experiment is the procedure that gives us this set. So what we're going to do here is we're going to talk about sets in some way that allows us to think about how to count the number of things in sets, how to represent sets, and how to perform basic operations on them. So first of all, what we call a set is a collection of objects, or we call them members or elements. All of these are interchangeable. So a set can be numbers, it can be dice, it can be the side that a coin lands on, but we represent them all as the set that we're interested in. So as an example, when you select a ball from an urn that has a certain kind of ball on it, like for instance, maybe you can only get white, blue, and green balls in this urn. So here's our urn. It's a terrible drawing of an urn. Please excuse my drawing. So then we have, I'm going to use gray here for the white, and then blue, and green. Okay. So these are the possibilities, even though there may be multiple of each, right? So if we wanted to dissect it even further, right, we would say, okay, there's first white ball, the second white ball, third, there's another blue, another blue, another blue, another green, another green, another green, to indicate that there's 9 of these balls in this urn, okay? And it depends on what it specifically we're looking at. Are we looking at a specific ball or the color of the ball? And we use these brackets to denote that this is the collection of elements in that set. So we say an element belongs to that set if it's in the set. So if it's represented in the set. So for instance, 1 is not an element of the set of real numbers such that x is greater than 2. This is another way of representing sets. We might call this set builder notation, where we have something that we're representing, x being a real number, and then we have some condition attached to it. So 1 is not an element of the set, but 3 is, right? Okay, so when we're talking about sets, we're going to be using, lots of different kinds of experiments with all sorts of different objects that we can represent. For instance, let A represent a dominant allele of a gene, and little a, so I have capital A and little a, representing a recessive allele. And our set of possibilities will be little a, little a, little a, capital A, little a, double A, each one coming from the pair of alleles, one from mother and one from father. And we have 4 possibilities there because we could pass down a recessive or a dominant from either one. But so that's, the basics of how to represent a set. But what about the size of a set, right? So what we call cardinality is the size of the set, or the number of things in that set. So in this example, right, if this is our set S, capital S, then we have 1, 2, 3, 4 possibilities. Here's another example. A coin is flipped 3 times. Each time we represent what result we got. So if S is the set or the sample space of possible outcomes, what is the cardinality? Well, we can think about it a couple different ways. First of all, when we flip a coin, right, each time we get heads or tails. So we might get heads all 3 times, or we might get heads the first 2 times and then tails on the last one, or tails in the middle, or tails last. Or we could get 2 tails after a head, or just head in the middle, or maybe it's 2 tails and then a head. And then the last possibility would be all tails. So we could represent our sample space like this. But, this isn't all that feasible if we do this every single time. And what if it was flipped 10 times? Then what would we do, right? Well, then we could recognize that for each, so really what we're looking at is we're looking at a sequence here of 3 possible spots where each A1 or AI, so either the first, second, or third, is, and this symbol right here, okay, represents, is a member of, or belongs to, we're going to reference an even smaller set, heads or tails. So each spot has 2 possibilities, and so we can think of this as being the size of that set, the cardinality, would be 2 raised to the power of how many flips. So if we flip it 3 times, that's 3. that's 2 to the third. That's 8.